The last worksheet of this unit focuses on problems that combine energy and momentum into the same problem. These can be challenging. These are the type of problems that they absolutely love on the AP test, and they can be challenging because it's hard sometimes to recognize when do I use momentum conservation and when do I use energy conservation. The first type of problem we're going to look at is relatively simple, and we'll work our way up to a more complicated one. But first type of problem might involve a collision. So let's say we had the typical boxcar collision, and we have one boxcar moving towards the second boxcar, and they collide. In this case, let's say it's an inelastic collision, and they hit, collide, and stay together. So they're going to move together afterwards. We learned how to do this in conservation of momentum. It's fairly simple. But you can add on to a problem like this a second part that might say, okay, well, how much energy is lost in this collision? One of the things that's true about an inelastic collision is there's an energy loss here. The vibration that happens when these two objects hit each other will convert some of that energy to heat. Once you're all said and done and you've found all the speeds that you need to find using conservation of momentum, then it's very much a simple matter of calculating the loss of kinetic energy. So the kinetic energy that's lost in this will be equal to the kinetic energy final minus the kinetic energy initial. The kinetic energy final in this case would be m1 plus m2, excuse me, 1/2 m1 plus m2 times that v final squared. And the kinetic energy initial is going to be the sum of the two kinetic energies. And you have to calculate them separately. You cannot subtract their velocities and then combine them. You have to literally do 1/2 m1 v10 squared plus 1/2 m2 v20 squared. Once you calculate this, this will give you a negative number, which is your lost kinetic energy. A little bit of work, and it could be a little tedious, but it's not exactly hard. The next problem I'm going to look at is a very kind of famous type of problem called a ballistic pendulum. A pendulum is anything that's held by a rope or a chain or a string, allowed to swing freely, and a ballistic pendulum might be something like this. Imagine that I have a bullet that I fire at this block of, say, wood that's hanging from the ceiling by a rope. This bullet is going to hit the block in a collision. Now, when you hear the word collision, you should automatically think conservation of momentum. Once the bullet hits the block of wood is going to swing up to some height before it comes back down. Let's say in this case we know the length of this thing. We'll call this mass 2. We know the mass of the bullet. I'm going to call it mass 1. And we know that angle that it swings up to. So a very typical problem like this would say, if the bullet strikes the block, and let's say in this case it embeds itself in the block. You can also do a problem like this where it exits the block. That's a little more complicated, but we're going to just stick with the simpler case of it hits the block and embeds itself in. So I'll draw it embedded in over here and rises up to a certain angle. The question might be, what was the initial speed of the bullet? And here's how we're going to approach this thing. So first of all, I know that when the bullet hits the block, momentum has to be conserved. So I'm going to write that. Mass 1 times v10 plus mass 2 times v20. Now, since these guys are going to hit and stay together, I can write the right-hand side as m1 plus m2 times that v final. The pendulum itself, the block of wood, was at rest. So this term is going to go to 0. And I find that this expression remains. Now, what I also know is that once that bullet embeds itself in the block and rises up to that final height, we have a speed change and a height change, which should just absolutely scream to me that conservation of energy is going on here. And so I know that at the bottom, the bullet and the block together, upon the collision are moving. So they're going to have kinetic energy. Now this is where it gets tricky, because this final velocity of the collision is now the initial velocity of the second part where the block rises up. But I'm going to stick with the F since I already wrote it once. Now when they reach their highest point, we're going to have all potential energy. So we'll have that combined mass, which we'll see in a second doesn't really matter, times GH. The reason we can see it doesn't matter is that these guys cancel out. Because this is one of those types of problems where we know the length of the string and the angle instead, if you recall back in previous videos, I said that the height in a situation like this is equal to the length of the string times 1 minus the cosine of the angle. So we can actually plug that in. What we wind up with is that 1/2 V final squared equals G times L times 1 minus the cosine of the angle. Now, between this information and this information, we can work our way back to the initial speed. If we were given the length of the string and the angle, you could see that we could first off solve for this speed right here. And then if we take that speed and put it into this equation, it should be no problem to go back and solve for the initial speed of the bullet. This is a typical ballistic pendulum problem, which is a nice example of how you can combine conservation of energy and conservation of momentum into one problem.